Today we will discuss topic lasing. So in this topic lasing we'll discuss about population, inversion, light amplification, condition of lasing threshold, and threshold current density. So these four definitions we are going to discuss under the topic lasing. Now basically lasing is light amplification. We are doing light amplification to achieve population inversion. Population inversion means we have two energy states, lower and higher energy state. When the number of electrons in higher energy states exceeds number of electrons in lower energy states, then the condition is known as population population inversion. Okay, now to understand lasing in deep, we must understand the equation of radiation of intensity of photons. Radiation of intensity of photons. So radiation of intensity of photons, in this there is an equation which gives relation between radiation of photons to I naught exponential. We will discuss that what are these terms: gamma function of photon, alpha function of photon, z. Let us say this equation is equation number 1. Okay, where alpha bar is effective absorption coefficient of the material in optical path. Gamma is optical field confinement factor. That is, it is a fraction of optical power. Z is distance. Z is distance. I are intensities. I naught is intensity at the starting, and Iz is intensity at the distance z. Suppose we have a cavity with two mirrors, let us say the reflectivity of mirror 1 is R1, reflectivity of mirror 2 is R2, and a light wave is traveling like this in this direction. So this wave is radiation with highest optical gain, and by this phenomenon we achieve optical amplification by feedback mechanism. Okay, that means the light which is entering here will amplify after traveling a distance L. Okay, the distance between two mirrors is L and it is traveling L plus L distance. Okay, so lasing occurs when the gain of one or several guided modes is sufficient to exceed the optical losses during one round trip through the cavity, that is Z is equal to 2L. Okay, so during the round trip only fractions R1 and R2 of optical radiations are reflected from the two laser ends. So R1 and R2 are mirror reflectivities. Okay, and also known as Fresnel's reflection coefficient. The formula for R is n1 minus n2 upon n1 plus n2 whole square. Okay, where n1 and n2 are refractive indices. From equation 1, that is our equation 1, intensity at distance z depends upon initial intensity. So from equation 1 we can write, because we know that z is equal to 2l, approximately equal to 2l, I naught, now it depends upon two mirror reflectivities R1 and R2, exponential 2l gamma minus alpha now we have modified our equation number 1. Okay, so at lasing threshold, that means steady state oscillation, lasing threshold, that is steady state oscillation, magnitude and phase are equal. That means the magnitude of intensity I2L must be equal to this, and the phase angle minus J 2 beta L is 1. Okay, so condition for lasing threshold, depends upon above equation. This one, let us say this equation is equation number 2. So from equation 2 and 3 we have, from equation 2 and 3 we have I 2L divided by I naught 1 upon R1 R2 is equal to exponential 2L gamma because of equation 3 we can cancel these out and taking log to both sides we get ln 1 by 1 r2 is equal to 2l now this value is threshold value a bar. Again we want to find out the value of gamma, which is alpha bar plus 1 by 2l ln 1 upon r1 r2. Okay, so this is the condition of lasing threshold. This is also known as GTH, the threshold value, and this can be written as alpha plus alpha end, where alpha end is mirror loss in lasing cavity. So for lasing to occur, G should be greater than equal to the threshold value. Okay, so the mode which satisfies the equation will reaches the threshold first. Okay, the last value or the last definition is of threshold current density, which is GTH is equal to beta JTH. JTH is current density and beta is gain factor. Beta is gain factor. Thank you.